This week, we're going to be looking at all of the various confidence intervals that we have. So there will be a total of 5 confidence intervals once we're done. You've already looked at 2. Technically, one of them has 2 versions of it. So maybe we should say that there's 6 confidence intervals. So the 2 that you've looked at, if you've looked at the single proportion last week, and you looked at the single mean. Now, when you looked at the mean, you looked at it for what happens when sigma is known, and that's when we use a z interval. So when we're using our normal distribution. What we found out that that is only if we know sigma, which sigma is the population standard deviation. So what happens when we don't know the population standard deviation? We talked about that last week, that you end up using a t interval. That what happens is that because of the approximation going on here, which that's s, so we're using the sample's standard deviation. So instead of the population standard deviation, we're using the sample standard deviation. And because there's no cap on that, on how big or small s can be, right? We don't know how the variance of our sample changes from the variance of our population. And because we don't know that, we don't know those 2 things, we have to be careful. And so in an overabundance of caution, what we use the student t distribution, and we use what are called t-scores for our multipliers. And if you've forgotten about this, go ahead and go back to week 2 and check out our stuff there. I also have at least one reading this week to remind you about the differences between t and z estimates. Okay, so what are we looking at? We're now the new things so those are the 3 that we looked at last week. You'd already seen 2 of them before, which was using the single proportion and the single mean with a z. It was the single mean with a t that was new to you last week. What's new this week is now we're doing differences. So our first one is a difference of 2 population proportions. So within one population, you might be curious about how 2 proportions that reasonably could be measured together might differ. But more than likely, what you're really curious about is how 2 different populations have their proportion, proportions differ. So it might be an opinion poll is a really good example of that. So maybe I'm curious about how Washington and Oregon, maybe we both have the same law on the books coming up. And I want to know, is it more favorable in Washington, or is it more favorable in Oregon, or is it about the same? So there is an example. So I have 2 different populations that I'm looking at, and I'm looking to see, and I have one variable, and I'm checking out that variable against my 2 proportions. Just some terminology. We've got our parameters, which is our P1 and our P2. So that would be the actual populations proportion. Again, that's something that we usually don't know. We usually don't know our parameters, whereas what we do know is our statistics. So what you're going to go do is go out and sample one population and sample a second population. Now notice, because I have an N1 and an N2, those are my sample sizes. My sample sizes actually do not need to be the same for this. So here, my sample sizes do not need to be the same. But all of the conditions that we had for a single proportion are the same. It's just now I have to have it for both of my samples. So once again, both my samples need to be random. And for each sample, I need to have a big enough sample that I should theoretically be getting 10 successes and theoretically be getting, I should be getting 10 successes and 10 failures. Now, why do we not use T for proportions? Because look, we know that we're estimating using P hat instead of P because we don't know P. We looked at standard error on proportions, and we saw that it maxed out when our proportion was at 50%. And so we actually have a cap on the amount of sorry, I had a brain moment where I couldn't remember the word variation. We have a cap on the amount of variation that that a proportion can have. And you can go back and check that out in week 1 when we discuss that. Okay, so in general, there are 3 guiding principles within confidence intervals that we're going to use. The very first principle is that if a value is not in the confidence interval, then you can reject that as a value for the, I thought I got rid of them. That should say parameter. Thought I fixed all of them. I guess I didn't. That's true for any confidence interval. So if I do a confidence interval for a single mean, a single proportion, difference of means, difference of proportions, difference of paired means, any of those, what I'm going to say is if a value that I'm curious about is not inside of my confidence interval, it's not within that interval, then you can reject it out of hand that it would be it would be a acceptable value for that particular parameter. Whereas if my value is inside of it, then it is an acceptable possibility for that value. Now, because of this, because that's our main guide of how do we deal with confidence intervals, right? The value's inside, then we say, yeah, that's acceptable. If the value's outside, then we say no. Is something weird kind of crops up. Is that, and at first, this makes a lot of sense. So we say that if I'm taking a difference of parameters, so a difference of proportions, a difference of means, a difference of paired means, and 0 is not inside of my confidence interval. Just take a second and think about what that means. So here's my number line, here's 0. If my confidence interval does not cover 0, then it's either fully positive, or, sorry about the yellow not showing up that great, or it's fully negative. I have one of these 2 choices. Now, they don't have to be so close to 0, they could be much further out. But one of these 2 things is happening if I don't cover 0, right? If I have wholly positive, then that's saying that the first value is the larger value. So if I'm wholly positive, that's not how you spell that, positive, then p hat 1 is bigger than p hat 2. Or when we get to means, x bar 1 is bigger than x bar 2. And because of that, or not even that, because this was so much larger than the other one, what really happened is it's insinuating this. It's insinuating that the parameter is actually bigger. It's a little bit nicer when we do paired differences. So we're saying the first thing is the larger of the 2. Whereas down here, I have a wholly negative interval. And now this is suggesting, because we look at it as P1, we're approximating this, right? This is what we're approximating P hat 1 minus, or sorry, P1 minus P2. And so if I'm fully negative, that means that this thing is winning out, right? This will only be negative if P2 is the larger thing. So this is then insinuating that P2 is bigger than P1, or that mu2 is bigger than mu1. That is, that the second parameter is the larger of the 2 parameters. So we're actually seeing so not only do we know which one is bigger, or not only do we see a difference, but we can tell which is bigger. Okay, so then what I think really confuses students, so that makes sense. If we don't cover 0, 0 is not in my interval, then it makes sense that I can make these claims. Now, what doesn't make sense for students is that so the other way that we could have done this is by taking a confidence interval for each one, so a confidence interval for P1 and a confidence interval for P2, and looking to see if the intervals overlap or not. If they don't overlap, then you can say it makes sense that there's not a difference. But if they do overlap, we can't make any conclusions because I don't know, is it the part where they overlap where the two are agreeing, or is it where they don't overlap that I should be agreeing with? Because the thing is that any value inside of my confidence interval is an acceptable value. So even values that seem very extreme, they have just as much of a probability as any other value. And I think what messes with us is, so for example, if I had an interval like this, right? And then there's just a teeny tiny bit of overlap. Well, because there's only a tiny bit of overlap, students are like, they're probably different. We can't say that. We don't know that. It could be that little bit of overlap is just as likely as all that other bit of not overlap to happen. So when there is overlap, we can't say anything. We can't make a conclusion, which is why we usually just go straight to these differences of intervals that we can go right ahead. So what happens when we do this is that when 0 is in, when 0 is in the confidence interval for differences, I want you to think about what that means. Well, what that means, if 0 is inside of my confidence interval, that must mean I have one end of my confidence interval over here and one end of my confidence interval over there. Do that in blue. That's the only way for 0 to be within my confidence interval. Well, notice 1/2 of my confidence interval is saying that the first parameter is larger. The other half of my confidence interval, and I'm using the word half colloquially and not actually meaning 50-50. The other part of my confidence interval says that the second parameter is the larger of the two. So these two things are in conflict with each other. And when we have 0 within our interval, we default to saying that there is no difference between the two, that statistically, there's no difference between the two. Okay. What else do I want to talk about? You're going to find, so as we go along, so this is just the kind of general rules, and this is for everything. This is for my proportions. This is for my, my means. Again, you've seen this before. It's just reminding you that you're going to use a T instead of a Z. And that we're referring to this as our standard error. Here are the conditions that we want to meet for a T confidence interval. We're going to be using these conditions to meet all the other ones. So come back to these conditions right here to be able to use a T confidence interval. So to be able to use the T distribution. I want you to remember that when we're looking at our conditions, the conditions are the requirements that the central limit theorem is holding, which means that the sampling distribution that we would be creating would be creating a nice bell-shaped distribution for us, which is how we can make the inferences that we're making. Okay, for once you've gotten used to that, now you can come to the idea of paired data. And I will make a separate video about paired data. The idea with paired data is that here's kind of the main take-ons for paired data. So I could do a before and after measurements on the same person or the same object, whatever it is I'm measuring. It could be it could be a before and after of like a regiment, or a before and after, or during various times. It might be under different conditions. So maybe I want to know how people are at test taking while listening to classical music, and maybe I want to know how people are at test taking while listening to, pick your favorite loud, really like bassy music. Maybe I'll do that. Maybe I want to know, I don't know, maybe I want to know how people are at test taking in the morning versus test taking at night. I don't know why I'm focusing on test taking. It's an example. Oh, a fun one is to measure people when they're standing and measure people when you're laying down. You actually gain a teeny tiny bit of height when you lay down because you don't have gravity pushing down on you. So you actually extend out. Cool fact. You get taller when you lay down. um, let's see, it could be, so that would be the same measurement on the same person or object under different conditions. You might have, this is probably kind of the hardest one, is to take similar individuals and to pair them and give them different treatments. So this would be done in like a hospital setting for testing pharmaceutical purposes. So you might pair people by the their already known conditions, or you might pair them by age and gender, right? So there's some reason that you're pairing people up, and then you're giving them different treatments to see how they react to it. And the reason that you would do that as opposed to one person and seeing how they react different ways is that you might just not, it might not be valid to do the experiment twice on the person. Or exposing them to two different drugs would, make, if one might be a placebo and one wouldn't, in which case it wouldn't make any sense to do that to a person, because you want to see the overall, the long-term effects of that drug, as opposed to what are you like it on it, then off it, on it, then off it. Okay, the last thing is two measurements on the same person. So my favorite example of this is measuring your upper arm and measuring your forearm, and go like this right now, and you can see, oh, my forearm is slightly shorter. I'm always curious about what the actual difference there is. So that's one to do. All right. Again, I have more reading about paired means and more on how to do paired means. So paired means take a little bit of work. You're going to get something called so you'll have a bunch of data. You'll have two data sets, and then you'll have something called D bar. And what you're essentially going to do is you're going to take that paired data and subtract and come up with a third column. And it's that third column of the subtractions that you are going to do your analysis on. So you will create the mean from that column. You will find the standard deviation from that column. So notice these subscripts, that S sub D, because we want to let ourselves know that while it looks like we're dealing with a single mean here, we've really gone and done this through pairing data up. And that's why we're using these subscripts. Finally, you have your two population means, which is now some of those examples I had before could have been done as population means, or two population means. So oftentimes the drug one, so you have the people taking the drug versus the people taking the placebo, and you don't pair them up and you just have two sets of people. It is more often that you will see that versus them trying to evenly pair each person in each set to another person and in the other set. Whereas here I can have them separated, and I can look at the average effect on the placebo group and the average effect on the not placebo group. And then I don't have to deal with trying to see, to make it meaningful to pair two individuals together. Oftentimes that is really, really hard to do. All right, and then finally, this is just a recap of kind of walking you through some situations, reminding you that in each case, we have a population parameter that we are trying to estimate, and then what statistic are we using to estimate that particular thing. Go ahead and watch my my differences of example, and then I also have some videos up top in the calculator section to show you how to use some of our confidence interval calculators, because I'm not going to ask you to go ahead and calculate that by hand. I know I just skipped right over this. This is the standard error of the first group, or sorry, I'm sorry, the standard deviation of the first group, and you're squaring it. The reason that you're squaring it is because it's underneath the square root, which you can see we normally don't stick the standard deviation of the sample underneath the square root. And so to counteract that, we are squaring it. We're doing a little bit of weird thing where we're adding it together. Something that isn't mentioned here is that for our data, you want it unpooled. I'll have a discussion about pooled and unpooled later on in the term. For our class, we're going to have unpooled data the entire time, so you can just keep it unpooled. I also want to note that notice with two population means, just like two population proportions, you don't need your samples to be the same size. You can have different sized samples. It's only when you pair your data up that your sample sizes must in fact be the same.